Hello there. This assistance is for the last 3 problems from the web assignment. The videos were not originally included because this was first used during the beginning of the pandemic when those topics were chopped off of the AP exam, but now they're not. So for number 13, we've got a projectile fired from the Earth's surface. So it is definitely moving. And it's got a little bit of potential energy because it's at the surface of the Earth, not at the middle. And it's got a certain speed, and they want to know how far will it finally go. So basically we've got at first, at surface, we have kinetic energy and we have some potential energy. At some distance away, all that energy will get converted into just potential because it's going to like stop some far distance away. So we've got our usual equation for kinetic. We've got our usual equation for gravitational potential energy, and then the same one far away. These two terms are not the same because these two r's are not the same. This r is this great big distance here. So we can do this little bit of work here to solve for this r, this distance. The only little wrinkle is they ask you for how far above the surface of the Earth. So when you solve for this distance, you're getting this whole thing. You need to also subtract out the radius of the Earth. That will give you just this distance above the surface. That's it for number 13. Number 14, planet Roton. Sounds like proton. They give you a mass and they give you a radius, which we might need to convert. Attracts a meteorite that's initially at rest, so it's way, way far away. In fact, it is so far away, we're going to call this an infinite distance away. So because it is infinitely far away, we're going to say it has 0 potential energy. Because if you divide by a large, large number here, dividing by infinity gives you 0. So that it is going to slowly yet steadily be gravitationally attracted, get closer, 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 and go faster, faster, faster. So once again, we're going to do like a conservation of energy thing with gravity. And right there, we've got some kinetic energy and we've got some potential energy. And we're going to set that to 0 before. So we are pretty much, once again, going to do some of the same kind of manipulation, and I think we're finding the speed right there. Nothing too much else to do for that one. Yeah. And on to the last one. Now we've got an oscillating particle, some sort of harmonic motion here. One thing that's a little bit tricky is they give you a time on this axis, but it's only to like there. So if you want to get, say, the time all the way to here, make sure that you're going to double whatever they're calling this amount of time. So basically, a period is that whole time there. Similarly, be careful when you're getting an amplitude here, because an amplitude could be measured right there, or it could be measured right there. My picture is not to scale. And so they give you values for each of these little marks on the thing there. So make sure you read both of those correctly. Now they're asking you for the kinetic energy. So once again, we are still going to use our same kinetic energy equation, but it's a matter of what are we going to put in for V? Because they don't give us a V, we've got to sort of take the long way around to get that stuff. Well, we know that period is 2 pi over omega. So that means omega is also 2 pi over the period. So maybe we can get this omega by doing exactly that. Now, why would we want such a thing? Well, because if you recall, we will get a maximum speed, which will be equal to omega times a, and then maybe there'll be like the cosine of stuff in there, but we're really not going to worry about that because the maximum value of cosine is 1. So really, if we can get our omega and our amplitude to plug in there to get our V, we can then put that into there. And for part B, we're just going to take a look at the graph literally. How many times per per second is the maximum kinetic energy reached? Well, if say we just look at this stuff here, just that stuff, that's one whole period, and we have one peak kinetic energy there, and we kind of like have a half a peak and a half a peak there. So every single period, we're going to get 2 peaks. So you can think of it as we've got times per second. We've got 2 peaks per period. And so we can literally divide those 2 numbers, the value in seconds for the periods on the bottom, 2 divided by that. So that should wrap it up for the last portion there. Keep working at it. Do a good job.